Hello, we're back. It's been a while, as usual. It is the day before Christmas, and so we have some free time, not working today, and so I thought, let's go back to spending some time on this guy, right? Now, last time around, where we left off, we assembled everything in one piece, and then I was having issues where the Raspberry Pi kept crashing every time we started running the robot. And I think my conclusion after researching and like really just trying a bunch of stuff and getting frustrated was that it's a power issue. So the Raspberry Pi, the way we have it right now, and I think we have a schematic of these, but essentially these, right? So the way we have it right now, the LiPo goes through a buck converter, steps down to 12V to power the motor controller. The motor controller is also capable of providing 5B, and so I'm using those 5B to go into the Raspberry Pi. Now this motor controller board is a random board I got off Amazon, so I know nothing about it, and it's also a very cheap board. So I just, by default assume it's not great, and so it looks like this board cannot supply enough current to keep the Pi up and running. It also looks like the Pi draws more current than Arduino Uno, which is what I'm used to. But that I could have figured out by just reading some data sheets, because the Pi of course has good documentation. And so we were having these issues that even when the Raspberry Pi is connected, I was essentially losing power, because even my MacBook Air USB-C connection into the Pi was not enough to supply enough current. I think the MacBook Air supplies up to like 3 amps, and this needs I think 5 amps. And so, I said I was gonna order a bunch of stuff, and so I did. I haven't opened any, but essentially got a bunch of converters, more converters. Let's open one. So the idea would be that we need to supply, it's essentially these, right? So we need to supply, it's another buck converter. We need to supply the Raspberry Pi with its own 5V, it's 5V? Yeah, 5V, 5 amp power source. And we also need a buck converter to a 12V for the motor controller, right? So I was kind of like looking around, is it normal to have 2 different converters, for 2 different low voltage? And the answer appears to be yes, it's normal. Like a lot of robot projects that I could find just have multiple buck converters to power different electronics. So this seems to be a normal issue to have in robotics. And so, that's fine. To me, it just seems a little crazy. It seems like there should be a better solution. But anyways, the most obvious solution, there's a nut here. There's a nut there. The most obvious solution appears to be, just keep throwing more converters at it, right? And so I got this one here, which, again, all from Amazon, all very cheap. But based on what the Amazon page said, this should be enough to, provide, again, the 5V, 5 amp that the Raspberry Pi supposedly needs. Now, if we were to do this, right, so much packaging. If we were to actually install one of these on the robot, of course we would have to figure out where to package it. Little heatsink. We would have to figure out where to package it. Route a new connection, so change the hardness, 3D printed chassis, all that stuff. And I don't even know where we can fit this, right? Because our package is pretty tight already, and we want to keep it tight. So maybe we replace the big guy for two small guys, something like that. There's a few ways we could do this. But yeah, all in all, that requires a little more effort, basically, or that requires more than 0 effort. And in the interest of time, I would rather see if we can achieve, balancing with 0 effort. That's what I'm looking for, 0 effort. Because at the end of the day, I think this one is a sole issue. And what's more interesting is maybe the software side at this point. And at some point, we can have a hardware V2 type of thing, as we did with the robot dog, right? The robot dog started when the robotics started, like it didn't have any power, right? It was powered by a computer going into Raspberry Uno. Then we had to redo the electronics and all this stuff, right? So I don't have a slide for that. But yeah, essentially the early versions were essentially these Arduino Uno to servos that didn't work, buck converter that worked a little better. But yeah, so something similar is gonna happen here. I'm gonna cross this out, be like, this didn't work. Doesn't work. So yeah, maybe that's for later. I'm not entirely sure. You know how much more time we're gonna get on these. Getting time to work on projects is being harder. And I do like the idea of eventually polishing something better, because when you're polishing something, you can do things like spend time on fixing up the wires and making things look nice and a nice package that you can then share with the world. So I think that would be cool. Anyways, my other point was the quick and dirty way of doing this would be with these. So I bought these adapter on Amazon. Unfortunately, I can tell that someone has already opened these and used it. But yeah, so this connects to the power outlet on my wall, and these should be able to provide power to the board, right? So we can connect these right now and get going, is essentially. So that is my plan for today, connect these and get going. Then we can go back to the software. Let's see. And yeah, if this doesn't work, then I don't know. I mean, you could blame it on this off-branded wire or something. Alright, so we have that. Now before we get into that, I want to do a few things. First, you know, we usually share cool links, and I have cool links today to share as well. So let's see. So I want to share a few things that I found this week. This one here, I don't think I've shared this one before. Let's see. Yeah, I don't think so. Alright, this is a robot from Stanford, and what I thought was cool, and you can see the video for yourself, but what I thought was cool was here, right? So they use tape measures as an actuator, right? So let's see. There's a part where they demonstrate this. I don't know if it's not playing, or there's a video somewhere they will demonstrate this. Oh yeah, here. All right, check this out. Tape measures, right? Tape measures are flexible. You can get them in. Yeah, you see how they can move them with the actuators there on the side. And this is my favorite part. Look, they're gonna move the ball closer to them. Yeah, that's cool. It's like a conveyor belt system. They can rotate the ball. I thought that was super cool. Super creative application. I like that. I'm gonna share that video. Of course, in this video, there's other things, but yeah, that's the one that caught my attention the most. But all of it is good. Thumbs up. Good job, Stanford Online. All right. Next, I wanted to share a paper that Disney put out. So Disney, of course, first video I've ever made was on Disney's Star Wars robot, the bipedal robot. And Disney has kept working on it, right? So Disney, as a robotics company, yeah, perhaps a little underrated. They put great content, and they're starting to move robots into park, kind of like into amusement parks, right? Kind of like when I applied to YC with the idea of VUCA, of making robots for entertainment. My idea was not probably a little raw, but these guys are kind of acting on that, right? So robots in real life as entertainment, for them it's a little add-on. Of course, they already have the entire park, right? But it's very cool to see this. Anyways, they put out this new paper, and the reason I'm sharing this paper, first of all, the paper as a whole is very interesting. But image 3 in particular, this guy, I'm just gonna paste the entire image. I thought it was super cool. Alright, so you can see here the schematic of that Olaf robot, right? If you don't know Olaf, I guess it's a character from Frozen? Yeah, Frozen. And you can see here how they build it. some of the joints. Its arm has like tweak arms, and it's like super complex or interesting mechanisms. You have the here bottom right revolution actuator axis. Yeah, so those are interesting. You can, if you zoom in here around here, right, you see a servo motor here, a servo motor here. And my favorite part is they tell you exactly what actuators they use, right? So for the arms there's Tina Mixel HG430V10, two of them, right? So you can just Google that, and you can essentially get these for yourself, right? Pretty cool. Legs are using Unitree stuff, smaller, bigger on the hips, makes sense. The neck also Unitree. The eyes you can see here, it looks like a single, does it say? It's a mechanism, it doesn't say how many motors. Looks like maybe one motor, another dynamic cell for the eyes. And maybe, I remember they said the mouth, and on some interview they said the mouth was also pretty, yeah, the mouth, also one actuator for the mouth, one for the eyes. So anyway, so I thought that was cool. And you can also see how tight of a package this is, right? There's so much compressed together. And on the outside, you can't really tell, it's just a character shape, but there's so much stuff compressed in there. I thought that was pretty cool. And it's like, kind of reminds me of this guy, or just the importance of having a tight, very tightly integrated package. Yeah, you can see the battery takes a lot of space, of course, and it's probably also the heaviest component overall. But they don't say if they have. Do they say? They don't say. They don't say if they have different a lot of converters. I mean, they might have a power unit thing that outputs, the specific power for everything. Also, the wiring through this thing must be like super interesting, right? Because all those actuators are probably daisy chained. There's a bunch of actuators, and you're gonna have to go up and down. You can see you have a Jetson computer in the belly, but of course you need wires going all the way to the head, right? Because there's an actuator there, and you need wires all the way to the legs. And it's tricky because the wires on the head have to make it through the neck where there's an actuator, right? Where it's that Unitree motor. So. It is very cool to see this kind of stuff. It's very cool that they're sharing. They don't have to share this stuff, but they do. That's cool. Let's see if we can see. Yeah, the neck there is not. It's a little exposed there, actually, the neck. Yeah, you can see some stuff. Well, of course, this is probably a prototype, right? But still, super cool. Super cool. I'm falling asleep. The tape measure as actuator. Okay. And then I have one more link here for you from Physical Intelligence. Of course, very famous AI lab in San Francisco. They put up some stuff. Yeah, put up some stuff this week. New stuff this week from 2020 December. Yesterday. There was some stuff even earlier, I think. Essentially these, right? Started all the way back in December 16th. Properties of VLAs, like, okay. Yeah, it shows the model learns to align human videos and robot data. This uses a simple way to leverage human videos. It can actually learn from human, okay. So basically, the model first learns to control the robot, and then it can watch a human video and replicate that using that same robot. I think that's my understanding. I mean, if that's true, that's pretty cool. I also think it's interesting, this camera placement. Reminds me a lot of Sunday AI, right? Sunday AI's camera placement. Oh, not the careers page. Sunday AIs, yeah. So camera placement here on the hat and on the hands there. It seems like these guys are doing something similar. Except I guess what's different here from Sunday or from anyone doing teleop is that this guy's generating data with his own hands, right? So he's not using. So Sunday uses a glove, and then a lot of the teleop stuff, like if you were using a SO100, you would have a gripper here and on your follower arm, and then your leader arm, you would have something that resembles a gripper, right? To move the gripper. Now what these guys are saying is essentially they can tube it, I guess, with human data as in like just hands, which seems to be a breakthrough. Anyways, I want to put that there in the video. I think it's cool, check it out. I have not looked super deeply into it yet. I also think it's mostly blog post. I wouldn't just brush it off for being a blog post, right? But I'm saying I'm not sure if there's stuff here that we can access. It's still very cool to see where things are headed. And there's talking about Robot Olympics, which would be pretty cool. Yeah. Making a peanut butter sandwich. Open jar, spread butter, cut the sandwich, and close the jar. Actually, that is pretty insane. Oh yeah, that's good. Oh, that's good. How it's able to cut the sandwich, interesting. And you see how it presses down? Yeah, that's funny. Peeling an orange. Are you kidding? They didn't demonstrate peeling an orange here, but oh, okay, here, peeling an orange. All right. I am not sure if the same human data thing applies here, right? Because of course they're using groupers here. Can we translate? I don't think we can translate from human hands to groupers. Oh yeah. I am not in. Is that what they're saying here? I mean, that is what they seem to be showing here. Yeah, I mean, that would be crazy, right? If you can translate video of people, someone doing something with their hands and translate to actions with groupers, I mean, maybe. But then to be able to do that for something like peel an orange, right? If you have fingers, peel an orange is a very different task versus if you have grippers. So yeah, that would be kind of crazy. Anyways, that's all I have for now. The other thing I wanted to say was that sorry, idea for the future with path planning, navigation. Anyways, yeah, the other thing I want to say, and I keep thinking about these every time I make a video and I make a stupid mistake, like not powering things correctly for the Raspberry Pi. I think about these because it is kind of embarrassing to make this mistake, but at the same time I think it's okay. It's good. It's a good trait to be able to like fail in public and have no shame, own your mistakes. But what's important about making mistakes is to learn from your mistakes, right? And not keep repeating the same mistakes. I think I've made some of the same mistakes over and over. And so I wanted to acknowledge that and improve. Right, so if we think about what has gone wrong with these guys so far, right, to date, like everything that has gone wrong, it's like, I mean, okay, list of things that went wrong, and I have a list. I guess I have a list of things to fix. So we can take that, right? So we have that electrical issue. Raspberry Pi doesn't want to boot. Solid red when relying on battery. USB-C fixes this, but need to check how to make this more stable. Right, so, okay, so that's the power issue I was talking about. And then things to fix on chassis, battery switch needs a mounting spot. Yeah, so essentially take all these problems and think, how could we have caught these problems earlier, right? So all these issues we caught once we had this assembled, right? Basically assembled, powering things for the first time, it wasn't working. So what we should have here is kind of like a product development or prototype development process that fixes these issues. And so the way I was thinking about this was kind of like a workflow, right? So first, determine what electronics are needed to meet specifications, right? So this is step number one, right? What do we need to make the robot work the way we want it, right? So these will be motors, these will be sensors, boards. Okay, right? So what do we need to make it work? All right. And then what do we need to power all of these components, right? So we should be thinking about power needs, right? So here we can start. Remember, when we first started, the first thing we did was lay out all the electronics and build a harness, and that kind of made sense, right? We could prove that it kind of works, but not perfectly. So determine what electronics we need. What do we need to power all this electronics? Step one. How much space does everything require, right? Everything require, not just some, right? Because, for example, we missed our switch. And then I guess the other thing, I usually think about it as in like 3 columns, right? Mechanical, electrical, and software, right? So top one is electrical, middle one is, you could say, mechanical, and then the software one, how will everything talk to each other? All right, so these are the 3 things that we need to think about before we build. And so if I was to, what do we need to power all electronics? Be like minimum, so voltage, voltage requirements or voltage ranges for each of them. So I'll say voltage range for all components. I would say current required for all components in all states. For example, motors running, or all motors running. Motors running are Raspberry Pi thinking, or running a process that apparently the computer is so powerful it draws current. Voltage, yeah, I think that's basically, at least that's what all I can think of right now, of course. How much space to require? Right here, it would be things like, do we have 3D CAD for all components, right? So last time around, we didn't have CAD for the switch, and that's part of the reason why we kind of like forgot about the switch. But we should not forget about the switch. So, so there's that. And then how will everything talk to each other? We haven't had a ton of issues here. I think this has been the easiest one, but make sure to connect everything and run it prior to assembling it on the robot, right? As a shakedown, I guess, right? So I'm gonna write shakedown. Yeah, it would have been better if we would have figured out our power issues before we assembled the robot. And so for that, the only way we could have achieved that was, first of all, having all the power figured out and built, but then having the software running, right? Because when we were not running things and we were just powering on things were working. But it's when you're running things where your current requirement increases and things start to fail. let's see, what other mistakes did we make here? Motor control hold didn't line up with chassis. Okay. See, I'm not sure, you know, for some of the stuff we had CAD, but the CAD wasn't good, right? And that's kind of like what happens when you buy things from Amazon and then you're relying on some model on RepCAD. And it's like, I guess you could validate the model, but also, I mean, maybe the lesson here is just buy nicer stuff, which has models from the manufacturer. Battery bracket should not use fasteners. Yeah. Wires to the motor controller. Do we have to think of wiring and where connectors will feed in point? And then the other thing here, I was gonna say, try to minimize fasteners from the get-go. Can always add more if something breaks. Yeah, and then I'll add something here. Things to do before assembling a robot. Yeah, I mean that basically sums up what I was thinking. Yeah. And now I guess I'll just see. Let's see if this works. Let's see if we can, if our new power source works, and then I'll switch the camera if this works. But right, so you connect it, and you can see here just from this connection alone, even my motor controller is lit up. I could potentially maybe even run the motors, even though I should not, but even my buck converter is lit up, even though my battery is not connected. So that is how much of a better power source this is. The only issue, as usual, is going to be that the wire is very short. But it was the longest one they had. Wait, maybe I have an extension. Extension cord. Alright, extension cord. What was interesting there was that the Raspberry Pi, I'll show you, right? So, look here. Oh, never mind. I understand why. Let's have the battery on. Let's have everything on. Okay, so here, battery on, Raspberry Pi showing red light. I connect this new power source. It kind of smells. Alright, anyways, I thought the Raspberry Pi was going to recover. It did not. But then if you reset, then it recovers. So that reset button is finally working. Yeah, let's see. So now we should be able to open cursor and pick up from where we left. So we have to reattempt the SSH connection. This is not it. So let's see, remote SSH, Super 23, Raspberry Pi local. Seems to be working. Password. Secret password. No, what is this? See your hearing code. Everyone's doing one of these days. But these are just, this is not me, this is just 38 million tokens. I don't think that's much. Yeah, it's not much. And you can see here it was only start figure. You experiment with 2 models. What else might go to? Claude 3.5 sounds right. That's old. That is old. Or auto now. Yeah. Sounds about right. I mean, this would be cool if I actually use cursor that much. 13 times. You got started building cursor, longest streak. How long? 2 days? 2 days, yeah, not very long. Alright, anyways. And been here, be at a cursor for more than 2 years, or 2 years. Which is crazy to think about. Doesn't feel like that long, but alright. There was one more thing I wanted to do, which was, you know, I think we would jump into AI generated code too fast, but we should talk about what's actually, what their code is supposed to be doing, right? So how PIDs work. And it looks like, so we have the, I think, let's see, is that a good, let's see if this is a good, so we have, alright, so if we're starting from left to right, so we have we're adding angle 0, right, a 0 as in like straight, let's say 0, and then subtracting the measured angle, right, and that gives us an angle error, or that is like how far from 0 we are, right, and that will be our PID angle. And then motor target speed will go here and here, turn speed. So this is assuming there's 2 motors, left and right, which is correct for us, right? Turn speed, okay. Speed error, that measured speed. I don't think this is correct for us, since we're not, yeah, we're not really controlling speed. I think something more simple, yeah, I think this is something more simple like this. Right, so we have target angle minus our current angle gives us our error. The error goes in here, PID terms. So here it takes the error and does a mathematical operation, PID, and then takes it out here, sums all of them, and that generates our output to the motors and then feedback, right? So I think something along those lines makes more sense, right? And so let's rely on graph here. I have a self-balancing robot with 2 motors. I think my PID loop looks something like that. I have 2 motors and an IMU to measure the angle. Can you explain what happens at the PID blocks, right? So it's gonna be a mathematical operation, but depends on what, right? So the P for proportional, I for integrated, D for derivative, right? So D will act on the error rate of change, P on the net error, like this is my understanding. And by the way, I should know this, of course this is from basic school, but it's been a while. Okay, so the P block, this reacts directly to the current error, right, proportional. It multiplies error by a constant gain factor. Right, okay. I accumulated the error over time by integrating, summing it, and multiplying it by focuses on past error that haven't been fully corrected. This accumulates the error over time. Okay. How does it achieve that? I'm not sure. In your robot, yeah, when it does, it eliminates persistence offsets versus steady state and then derivative. This breaks the feature by calculating the rate of change. Okay, so for both I and D, this implies that we have not just a current data point, but also a previous data point to be able to calculate a rate of change. For I and D, these imply that the PID is running with more input than just the current loop, right? There has to be a memory component. The IND requires historical data from previous loops. That's why PID controller is set to use memory or state, right? So the integral accumulates error over time. In code, you'll see integral plus equals error. So it'll be sum the error, but the error times delta t. Alright, so now we can go back to cursor. See the robot ls. Alright, so in here, which was PID? Was it PID? I don't even know. Why do we have? Oh, because I was making changes. I think it was self-ons. Alright, so here, I think it's basically the same. Okay, so here we should see, where do we use ki, for example, right? Where do we use ki? Now it's defining ki. Ki equals self plus self integral max min. Okay, okay, it's limiting the integral. Okay, and then we have self integral plus equals error times delta t, which is exactly what we're seeing here. Yeah. Maybe we copy these here too, right? So I just want to make sure we understand what's happening, right? Not just relying on the AI blindly. All right, so inside the loop, error equals target angle minus current angle. We've talked about this here on the left. Self integral equals plus minus error, derivative error minus previous error. Okay, so self integral basically adds up the errors and derivative. So self integral is going to just increase over time. Is that a question? Because the error could be also to the other side, right? So error could be positive or negative, right? Question mark. Does this mean that integral will always increase over time, or can it even back to zero, assuming error can be both positive and negative? Right, so I think it's a valid question. No, the integral does not always increase over time. Here's why. Integral term is. Alright, so there can be both positive and negative errors. So yeah, okay. Derivative error minus the previous error. That makes sense. Over delta t. Okay, and then p outs. Okay. Alright. And then I guess one question that I would have for our code is, how does the total output, like when do we use compute? How does this total output, PID output, right? Motor speed. Set motor speed. We have a function called set motor speed. Alright. These all seems to make sense. And so I guess we can try running this. I don't know if this is gonna work. Okay, Alright, so here you see that I think we're supposed to be reacting on. First of all, this thing shakes a lot. We're supposed to be reacting on the roll, right? So there, I'm just gonna roll it to 35. But beyond 45, it shuts it off. And then here the other side, 18 and so on. And then 0, kind of like somewhere here. But you can see here that it even reacts to small numbers of 0, right? So we're a little jerky. I know that looks terrible, but you know, I don't think it's too far off from what we want. And then, yeah, it looks very bad. So my hand was in front of the camera. It's kind of self-balancing, right? Kind of. Oh, it's not actually. It's touching. Yes. I'm gonna pause that just because things are gonna get very hot. Motors get hot. Motor controller kind of hot, and the Pi gets hot for no reason. The Pi always gets hot. I don't know. Even though the computer's not that intense. But. So, from my point of view, here is where we can start to tune these with the PID loop, right? And it's just a matter of tuning our PID parameters, right? And so if we go back to what we had discussed here previously, by we I mean UI and Grok. Let's see. Right, so we have these. Let's see. So previously we said. So what did we see, right? So we saw a lot of jerkiness, right? So the proportional block effect. If the robot is tilting a lot, large error, P increases a strong correction force to back up upright quickly, right? So okay, it eliminates persistent offset. There was some persistent offset, and I don't think I was doing anything. And then D, it acts as a brake to dampen rapid changes, right? So to me it's very jerky. So I think D can be higher, right? And so we can attempt to go higher. Now what's higher, right? I think is 2 to 3 a lot. I think that depends on your system. And so we went to 3 here, 3. Is that better? I mean, I would say it's not a big change, right? Not a big change. So now I might go with 5, right? And remember, we started at 2, right? So I might go 5. Alright, I want you to be able to see this. It doesn't really count if we're touching. So I would still say very shaky, and if my understanding of D is correct, then we just keep increasing D. And did you notice any difference in behavior? I would say not really. Gonna go back to D. I am now remembering that I think there's something to be said about always starting with K. With P, sorry, so the proportional. So let's start with going back to 5 on the proportional. First of all, we always seem to be leaning towards one side. I just need to figure out which side that is. Motor control is getting hot now, guys, by the way. Alright, so here, I think there's a slight offset. So I think we have a parameter to set the target angle. It's going to set at 0. We had it at -5. Yeah, I think this is working pretty decent. Okay. The heatsink on the motor controller is getting hot. Okay, what happens if we drop the P even more, right? What happens if we drop the P even more? What I say happens is it's trying to correct, but the corrections are not big enough. So P definitely needs to be higher, I think. So 5 didn't work, 2 it's not working. Let's go to 10. No. Let's go to 20. Very aggressive, very aggressive. Okay. Alright, let me do one thing here. I'm gonna set the maximum speed to 0 for a little bit. Just because I wanna see what the thing calculates at. So these, to me, looks like pretty flat. And it has, we have it at 4. That is reading 4 degrees. So I'm gonna set the target angle to 4. I don't know if it's subtracting the target angle or what. Let's see. PID controller. Alright, well. The other thing we can do here is max out the water speed, because we had it not maxed out, but alright. So see, now I can clearly tell that it doesn't want to, that it's leaning towards one side. So I think my target angle is a little too drastic. Even now, this target angle does not make a lot of sense. Let me go -2. And I'm just smelling because it smells like melted 3D printed plastic. I mean, it honestly feels pretty hot. Let's check battery voltage. I don't know, proportional 40. proportional just too high? Proportional 1. Is that why it's so jerky? Because its movements are too sudden, too strong. What would happen? Yeah, what would it look like if the proportional is too low? Like what would be? Maybe we should start by making everything else 0, right? So we are only dealing with proportional here. And see what that does. Right, so there the proportional is so low that it doesn't do anything. I could hear the motor winding trying to move, but not enough speed to actually move. Okay, so this is what a low proportional does, right? Oh look, it's balanced. Tip it over. I can hear it want to move, but it doesn't move. Alright, so that proportional is definitely too low. So now we go to 5. I mean, honestly, not so bad. I mean, it's kind of upright. Alright, you know what? It's a little crooked, but I think it's because my target angle is off. I mean, are you seeing that? It's actually working surprisingly well. Pretty good. I mean, I still think it's a little crooked. Let me try to fix this crookedness by changing the target. A little more. So what seems to have worked is setting everything at 0. So I wonder. Oh yeah, it looks much more upright. Pretty much upright. Let's give it like a little 0.5 here. Trying to figure out if maybe the wire is helping it stay upright. The other thing I don't want is it to be upright because of the switch on the back. It keeps leaning backwards. But okay, so it's upright there. Now the one thing you will see is that when it does need to correct, its movements are very jerky. But it seems to be able to correct just fine there. But it could be a little smoother. Right, so that's interesting. So they only PID to 0 seems to have worked. When tuning, I'm gonna have to check the work. When tuning my PID values, I started by setting I and D to 0, and now P equals 5 appears to work okay. The movements are a bit jerky though when correcting. What should I do next, right? I think, right, if we think of like jerky movements, that would be more D. I think D would be more for the jerkiness. I think I would, yeah, okay. Oh, actually, it's saying what I thought, D, okay. And it seems, as a rule of thumb, KD between 0.5 and 5. I wonder if that's because D should not be more than P. Low D is so jerky, or should it be good D, smooth and quick corrections, too high, sluggish to respond. Alright. So let's start by KD 0.1. Have we made it too easy on the robot? Okay, so I would say it's still too jerky. Alright, I'm gonna try to take small steps here. 0.2, right? So 0.2. A little jerky still. 0.3. And now we're in that sluggish. And you see that vibration there that I'm getting, right? Okay, well, yeah. You see that the jerkiness is back now, right? This is what we're saying at first, right? And so it seems like KD 0.3, we start to see jerkiness. At KD equals 0.3, I start to see jerkiness be under this value. Does that make sense? I mean, I don't think jerkiness is the same word that Grok is using, because Grok said like a lower one would lead to jerky. Start to see jerkiness or higher frequency twitching, shaking when you reach KD, and it gets better when you go lower. Means one thing. Derivative term is amplifying sensor noise from your IMU. Here's what's happening. Theoretical is rate of change. IMUs typically cheaper. How dare you? Always have measurement noise. This wasn't cheap, okay? Grok. When you multiply the noise by KD, it turns into rapid, yeah. So KD damping benefit is starting to be outweighed by noise amplification. What to do next? Lower KD, sure. Filter your angle. This is the most effective fix. Add a simple low pass filter. Alright, so I thought we already had a low pass filter, but sorry, let me start by going back. Maybe I'll start 2.5. A little bit too jerky there. You see how it swings a little bit? Okay, of course the jerkiness is not welcome. But also I wonder if I start from the ground, can it self-correct? Oh yeah, it can. That's neat. It keeps, my table's not big enough for this way. Okay, those things we're seeing there, I think that's where I comes in. But for now, I think we still want to even lower KD. I'm going to try 1.5. I do agree with what Grok said about the sensor noise for sure, but I might well put 2.1. Probably leave it there. Yeah, I wonder if our CG is too too low or making it too easy in the robot, honestly. It's a bit too easy. Okay, so I am coding in cursor. Can you come up with a prompt to get cursor to implement? Oh wait, a filter for the for the IMU's data. Compute derivative on PV, process variable instead of error. Oh. They also said slightly reduce KP. Let's try that. Huge swings there. I don't know, that seems to work good enough. Oh. Alright. I wonder, can you explain more about compute derivative? How is this different than the PID approach? Yeah. Alright, so now let me save this in PID. It's gonna, don't really need to because we have revision control of course, but I want to, let's see, oh, no, not use Siri. It knows we're here, right? Let's see. Alright. The unique derivative from PV, derivative from process variable, is a small but very useful modification to standard PID controller. This one I don't remember from school. It is especially helpful in self-balancing robots. Alright, so the standard, we've talked through it. Right, the derivative term looks at how fast the error is changing. Problem: if you suddenly change the set point, you decide to tilt the robot forward on purpose, the error instantly jumps a lot. The derivative sees a huge spike. It produces a large opposing kick. Yes. In a self-balancing robot, your set point is usually fixed at 0. That's right. So this is an issue to normal balancing. There's a subtle problem. The robot is correct until a sudden change in measured angle affects both P and D in the same direction, which can amplify overshoot. Okay. Instead of deriving the error, you derive only the measured process variable, the actual angle from the IMU. So D is now measured angle minus previous angle. I am not sure. The derivative now measures how fast the actual angle is changing. Oh, I see. Instead of error. Yeah, because else error, huge error, previous error, huge D. The negative sign is added because if the robot is tilted forwards, you want to create upward counter. Why this is better for self-balance errors, no derivative kick. I mean, that's interesting, but I don't know if we need that. And then this is a filter, right? See, so true exponential movement average coefficient. Okay, so it's these filters all produce high frequency noise. Okay, low pass filter for gyroscope critical for using variable noise. This okay, less filter and faster response. All right. So it's doing an exponential moving average, okay, and then low pass filter for final angle. Sure, I mean we can try. We can try. I wonder if it'll make the Raspberry Pi run hotter. Oh wow. This guy is like doesn't want to go anywhere now. Still a lot of swing, huh? You're swinging, dude. Pretty good. It almost looks like no. I need to put this on the ground. But it's not ready for ground yet. Oh, it's about to jump off the table. Alright, so I think, okay, I implemented a filter. My KP is now 4.8, my KD is 0.1. But my KI is still 0. I am noticing some large swings when the robot is trying to stay upright. I will go a lot towards the right, then a lot towards the left. Is this something that KI could help with? Right, and if we think of KI, I think this is exactly where KI or the integral could help, right? Because it remains a persistent offset of steady state error that P alone can't handle. Like, I don't know if that's exactly it, but for me, right, if we're leaning one side, right, for a long time, that's persistent error in my mind. So I would think maybe, no, the large swings, big oscillations, left, right, your experiment are not typical things by adding KI. In fact, big slowish oscillations where the robot overcorrects to one side, KP is a bit too high. Okay. Alright, well. Point 2 seems to work now for KD. I don't know, so we're trying to drop the KP. It seems to be doing better. Yeah, the issue is my desk is not even. It's still seeing swings, but also the more we drop it, it still seems to work. I mean, I'd say swings got worse there. Yeah, I'd say swings got worse there. Maybe 3.5 is their sweet area. So 3.5, what if we go increase this back to 3? 3 is where we set jerkiness, or we set jerkiness on the KD, that was before the filter. But now you see jerkiness again. A little bit of jerkiness there. Yeah. Some amount of jerkiness, so we go to 2.5. The robot is still upright on its own now. It's crazy. Nah, I think we're gonna go back to 0.2. We need to get that switch on board. Yeah, I wish it didn't swing so much though. That's the one thing I'd say. You know what? Maybe the jerkiness is better than these. Those swings are big. KP is a bit too high, I dropped it, not enough damping, K is too low. Yeah. I mean, I can give you like 0.21, 0.22, but. Do I even need KI here? let's go back to super high KD. It is tricky. Yeah, we can't do that. Yeah, look at that. No, we can't do that. But I don't know if I agree that a lower KP helped. Right, so we were 3.5, now 4.8. This seems to be better, in my opinion. Okay, well. I don't know, what do you think? Maybe 5 to 3.8. I know it was 3.5 before just now, but we have too much stuff dragging. I think we're ready to go to the floor. Just need to figure out if we need KI at all. You put out any KI at all for basic self-balancing animation. It's better to leave at 0. His Y KI is not needed for most hobby. Yeah. Alright, so maybe no KI, and we just move to the floor. But I do want to tape these. Maybe just tape it. Tape it like here. 1 second, I'll bring tape. Alright, yeah, so let's tape it so there's less things dragging on the ground. I mean, horrible to use tape, but. Alright, so now we have one less thing tacking. Now we only have kind of like the cable here protruding. Seems to be okay. Oh my, absolutely crashed into the, alright. Give me 1 second here to move things around. I'll give you guys a better view. Well, I guess I'm gonna watch through the camera. I'm gonna stay in the desk. Okay, so we have that. I realize this is not the best setup, but more space, just let it run. What the hell was that? Give you a more dramatic view. Alright, so it's actually balancing right now, right? So if you believe it. I guess I need to poke it or something. It's balancing too good. It's able to record it and touches the ground. Not a lot of swing, that's good. As I can just connect the wire. Alright. Yeah, I mean, floating with air made this too easy. I don't know, can we make it a little less jerky? Touches it around when it turns off. Oh, ow. What happened there? I guess it will run out of training now. Hey, don't chase. Alright. Oh, that's new. Tumble over. Alright. Alright, we made things worse there. By reducing KD apparently. Back to where it was. The wire seems to influence it a lot. Anyways, that's not bad. Alright, what if we drop the KP a little bit more? That's like we had before. Yeah, that big swing there. I mean, I'm attributing that to the cable. Yeah, it is possible sometimes when it tilts too much. That happens, right? So this is what Grok was saying, right? When it tilts too much and your error is too high, both your proportional and your derivative spike to the same side, and that can happen. Basically, you tumble over. But as long as there's no spikes, but when there is a spike, it's not very stable. Yeah, this doesn't feel like the most stable thing. Yeah, interesting. I mean, it honestly felt more stable when the KP was higher. So let's go back to that. Why is he doing that? 3.8. So really nice to work with Raspberry Pi and just being able to push the changes remotely instead of having to connect. Right. Oh, it went out of the camera. It's gone out of frame. Alright, I am curious to implement what Grok was talking about. Right, so I'm gonna self this here. And I'm gonna say I want to implement the process variable derivative that you described. Can you please come up with a prompt for a cursor agent to implement it to my code? Derivative process variable PID. Just a little confused that I've never heard of this one before, but also I wouldn't say I have a lot. I wouldn't say I know a lot of this stuff. So. The PID controller manually converts the desired target value set point with the actual value of the system process variable or PV. The difference in these two is called error. Is okay. So I want to switch to derivative on process variable instead of where derivative is. Okay. So balancing PID. Okay. We can try that because yeah. We need to run this guy with no wire to see how it's gonna behave actually on its own. And then it will be interesting to have like a higher CG, kind of like a coma body. Of course, these motors might not be powerful enough for something like that, right? But something taller, can we still handle it? It's the same logic, right? But all right. So PID controller. Let's see. Compute PID using derivative on process. Okay. Compute. Okay. Yes. Derivative changes. Derivative angle change. Okay. Integral remains the same. Okay. Good. I think it's good. Okay. Well, let's try it. No, we're still seeing the same behavior. I mean, the takeaway here might just be that our P is too high. I honestly like how it was before. And I choose to believe that our P is too high. Alright, so what happens when the P is too low, right? So I think this is what happens when the P is too low. Basically, it cannot correct. It's basically we're flipping over and bouncing. And then when the P is maybe too high, I mean, maybe a little jerky, right? And then let's go back to what happens with the higher Ds. Okay. Absolute jerky fest. Can't have that. A little lower, but still higher than what we had before. I mean, it seems to correct for that case where it just leans towards one side a little better. But it is overall a little more shaky. Interesting. Yeah, when you try to bring it forward with your hand, it feels a little stiff, right? It's like it won't go. Except if it's on that side. On that side, it seems to be okay with just freaking following that. Yeah, one side seems way more stable. more stable. This takes more force. What are we doing here? All over the place, dude. I like how it just dies and it tilts. Alright, so that KP might be too high. 3.5. But I mean, just there, it seems to get worse with time, right? The longer you run for, the worse it seems to get. Sorry, the tape came off. What are you doing, dude? What are you doing, bro? Relax. See, I like this behavior, right? It feels stiff. This side, now it's stiff. Why? Could be the wire. Could it be the wire? Hey. Could it be the wire? Could it be the filter? Filter alpha, typical range. High value, less filtering, faster response, more noise. No, that seems fine. I mean, I think as a first pass, this is what we're looking for. It's funny when it does that. Alright, stop the graph. 1 second. Stop it. You're gonna hurt yourself. Part of me wants to call this good and go prepare Christmas dinner, but part of me is intrigued. I didn't apply the derivative on the process variable. I tried it, but it didn't seem to make a big difference. I am still running with KP 3.5 and KD 0.2 and KI 0, but what I am noticing is a bit of a trend. The robot will start tilting one side and then keep going towards that one side without being able to correct to the other side before hitting a wall. In my mind, this means I should increase KD, but when I try to do this, the robot gets insanely jerky, right? That's what we see. Let's see what this robot thinks. Starting to tilt gradually to one side and next door in that direction without recovering sounds frustrating. Why does Grok talk like this? It doesn't seem quite match the large back and forth swings you had before. Instead, this points to lack of correction for small persistent errors. You see where this is going, right? It's going towards KI. Oh no? Improve filtering to allow higher KD. This is a key to reduce jerkiness. So I don't know. Increase KP again, but carefully. This strength, I mean, add a tiny KI to counter drift. Yes, yeah, it's in you. Check for non-PID issues. Dude, chill. I mean, no, tilt to sign check, tilt forward. Yes, of course. I hate when it makes silly suggestions. A little KI here. See what happens. I mean, I don't know if we can even tell. Hey. Dude. What are you doing? Are you drunk? I am not sure. One sec. Let me check that it's actually as you expect. I'll lose your camera so you can see it. After the motor starts spinning the right way, right? So here. Oh, this guy's getting cut up. The tape is coming out, right? Okay, so here, when we tilt a little bit this way, oh yeah, it seems good. The motors are spinning in the right direction. So if you spin this way, something weird is happening here. Let me read the code here. Derivative. I think. Okay, so Yeah, I think something weird is happening. Trying to figure out, but it seems like the motors might be spinning on the wrong direction sometimes. So we gotta check, right? But okay, so if we run this, right? So here, right? PID, we're at 0 basically. PID is like 5, right? And so we start tilting, PID goes positive. And go the other way. PID goes negative. But when we're tilting this, when we tilt this way, right, like this, the wheel spins this way, which means the robot will gonna wanna go that way. Why would it do that? But then it kind of works. So I guess the one thing I'd say is instead of printing the full PID value, I would like to print but also the independent PID values. Right, so I just want to see what everything is doing. I want to see if because we could either print or we could just remove PID one at a time. Actually, I guess I'll start there, right? So this is 0.25, 0.38, right? So we could just start here. Oh wait. Yeah, this should be a simple change, but alright. So we're here. Oh. Simple formatting error that AI will fix for us. Yeah. I'm looking for a robust solution here. Says as he continues to bytecode his way through this project, but alright. Sorry, camera's in the way. I can't see. Alright, so we can see here PID 48, P51. Right, so D is pushing us to the other side. Alright. I mean, I know this is super basic, right? But we all agree that if the wheels were to spin this way, I just don't understand then, right? Why are the wheels, when you tilt this way, your wheels should go the other way, no? Then it seems to work. Of course, I'm only looking at the D component when I hold it in my hands. I think, yeah, my KP is really aggressive here. The KI component is also kind of getting high. Let's get rid of KI. Alright, so this was kind of working last time. So, oh, you can't see it. Okay, so it kind of works. I don't know why the camera's being weird, to be honest, but changed. The robot just gotten more unstable. Yeah, it's holding there, but. Oh, sorry, I made KD 0 also. Didn't mean to do that. Sorry, don't let your ground. You can also go back to. It's balancing. It balances, but it could be a little unstable in the extremes. It seems to be behaving much better now. Let's see, when you pull the display, it doesn't resist, it goes along with you, and then it kind of corrects. So I think that's what I was seeing. Yeah, I mean, now it's pretty good. Now it's pretty good. Whoa. I think I'm gonna call it. We're gonna call it here. I think. I mean, it's doing the thing, right? It's doing the thing. It's doing the thing. Right. Alright, let's come back to the desk. This might be the shortest video ever. I think I was just planning to keep running into issues or something. Alright, so it's doing the thing. Throw what's doing the thing. Alright, so I think we need to start thinking about what's next, right? So we could fix a lot of the issues we have here, including powering the Raspberry Pi on its own from the onboard battery. So this thing can run on its own and we don't have to like have a harness and you just let it be. At the same time, for the next bit of work, I think we could either go neural network or what I think is going to be more interesting is, okay, keep balancing, but now let's have some user input, right? So I want to be able to control it, go forward, go backwards, rotate it, and so on. That's the next thing we're going to do, right? So we'll do hardware V2 and then this, all right? And for now, I mean, I really don't think I'm going to be able to work on it till after Christmas. Yeah, maybe we can squeeze in some work there after Christmas. But yeah, I think so far, very basic project, it's fun, but I want to polish it, right? I want to do something that we can be proud of, right? Like I said, anyone can put together one of these things pretty quickly. We used to do it in hackathons back in the day when I was in college, but I want to do something a little nicer package where I can put my skills to use and continue to learn things, right? So, I hope, as we're kind of like wrapping out the year, I hope to be able to work on robotics more next year. I think that would be something cool, something that makes me happy. And so, sometimes I look around my room here and it's crazy because, now I have this guy, now I have like the robot arms, I have like, of course, the classic dog here. I have other stuff, right? So from even before SO100, I have like a gripper that is 3D printed, open source, put together myself. I have a drone here with 3D printed components, which by the way, the US yesterday banned a bunch of things that on these robots. So there's a lot of things here that you can't no longer buy in the US. So this became more special. But anyways, I just keep looking at all the projects, right? And the library is getting interesting. So I definitely want to continue doing that. But I think it will be cool to have one thing to keep building on, right? So these little improvements here and there compound. So we'll see what that is. We'll see if this guy is that. It could be. Yeah, it's an interesting plan. But anyways, thank you for watching. So far, only I think 3 videos this year. But I mean, if there's anyone watching, even if it's just one person watching, that exceeds my expectations. So I'll keep doing this. I'll keep doing the type of videos that I would enjoy myself, and hopefully you're also learning something with me. Anyways, Merry Christmas and Happy New Year's.